take a look at some more damper actuators here.
Right, and to Carl's point, you can see the right-hand side is noted as normally closed, and there the actuator stem is connected to the bottom side of the axle. So as the branch line pressure increases, the stem is going to extend, driving the damper open. This fits with some great analogies to our valve actuators. You have to have the properly selected spring range. You have to have the proper amount of thrust to operate the damper smoothly. These are all parts of the selection process. For dampers that are very, very large, they can either be split and actuated in sections, or actuators can be tied to the same branch line to aid in opening very large or very tight closure dampers. But that's all part of the initial selection process.
Okay, let's move on then to damper actuators and how they may be interfaced to a direct digital control system or any kind of electronic control system. This picture on the left-hand side has main air pressure coming into the controller, as you learned in the last session, and then this pneumatic controller is outputting out of the branch line a variable air signal. In this particular case, it's 3 to 13 pounds psi, and that may be dependent on different manufacturers. So this then changes, modulating to full 3 to 13 pounds. At 3 pounds, then there's no air pressure on here. This rod would be fully inside the actuator, and as it's modulated from 3 pounds up to 13 pounds, the air pressure would build up and then open up this or extend out the stem out of the actuator. So now if we take the same controller as far as the air pressure goes, we now have air pressure of the main air coming into an EP, which is really, this is actually a transducer, electric to pneumatic transducer, that's going to convert the signal that's coming from main air coming through here and change this line going to 3 to 13 pounds. And it does so by changing, instead of having an air pressure coming in here, we are now showing a DDC or direct digital controller that's going to change the signal from 2 volts DC, modulating it all the way up to 10 volts DC, which would then be changing the air pressure going in here. And this is something that we see quite often where a direct digital control system comes in on top of an existing pneumatic control system, and in particular in the main air handling units, to be able to take direct digital control, electronic control, and still keep in the existing pneumatic actuators, either dampers in this case or valve actuators, because the existing cost, the capital investment, is already there in place for these actuators, and quite often the size of these pneumatic actuators can be pretty large size, and therefore this is a better application and a better solution to continue to use those pneumatic actuators.
Right, and you've probably seen this before with the electric actuator offering. To get the same amount of thrust or torque, quite often they get either very difficult to find or very expensive, whereas pneumatics can very easily and inexpensively give you a good deal of thrust or torque. So this really makes the DDC retrofit a lot more realizable.
Okay, we'll advance to the next slide.
Here we're talking a little bit about spring ranges again, and in this example we've got a 5 to 10 pound span spring, and as we touched on before, at 0 pounds the actuator stem is fully retracted. The spring, of course, is what's doing that. At 5 pounds or thereabouts, we'll begin to extend the actuator shaft to the point where at 10 pounds we'll be fully extended. Now, of course, there's going to be some opposing force on that actuator stem, and if that opposing force is greater than 10 pounds, that 10-pound pressure might have to rise to 10 or 12 before that actuator is fully extended. If a positive positioner were installed on this actuator, the relationship of stem to branch pressure would be maintained, because we could admit up to a 20-pound branch to drive against the backside of that diaphragm so that we'd achieve the desired position. There's different spring ranges shown on the left-hand side, but most of your economizers, your cooling dampers will have the higher ranges, the 8 to 12, 8 to 13. 3 to 13s are shown here as well, but that's uncommon for a full range of control. Again, it depends on the application and what other components that this actuator needs to sequence with as to what that spring range would be. So here we see something that looks very similar to what we did before with our air handling unit. But in this scenario, we've got an additional device to sequence. So as before we had just a heating valve and a cooling valve, now we have those very same valves with different spring ranges, but we've added a damper, a cooling damper. So picture that air handling unit with maybe an economizer on it, meaning we can take advantage of free cooling out from the outdoors if it's suitable. So as the space temperature in that application began to rise, our heating valve would close. And on a continued rise in temperature now, instead of operating the chilled water valve as we did before, we'd now start to open our economizer dampers to the outside. Our cool, fresh outside air would come in and start to cool the space down. If the air wasn't sufficiently cool or the space load was too high, the temperature in the space would continue to rise and our thermostat branch pressure would continue to rise, at which point our cooling valve would now begin to open at about 10 or so pounds. So you can see here how the spring ranges, again, are so important in sequencing the different products so that they all operate together to achieve your final control sequence. So now we get into positioners.
So we talked before about valve actuator positioners, positive positioners, and we also have the equivalent of those for the damper actuators. So we take a look at the slide and follow the cursor here, that on the side of this particular model, we have a rod and spring that's attached directly to the stem as it extends out of this damper actuator. So this is physically giving some feedback of where this is extending out or not extending out. It's actually giving feedback directly into this positive positioner. And again, this is a box that may or may not look exactly like this, but again, it has ability to be able to have main air pressure. Let's say for this sake of conversation today, this is, let's pretend, 20 pounds of main air. And then we have from the controller, we have the branch line air pressure from the controller going into the P port, which is the pilot port of this positive positioner. Then with this feedback spring, if the controller or thermostat or controller is saying, again, I should be at 50% open, if this stem is not extended out 50%, the positive positioner will say, hey, I'm not at 50%. I'm going to use 20 pounds of air pressure coming through this positive positioner. I'm going to send that out on the branch line to these two actuators, or three actuators rather, and be able to actually take the 20 pounds of air and move this stem against the airflow that's going against us, is not allowing this damper to be at 50%. So once this is at 50% and the controller says I should be at 50%, there's no more movement, and this positive positioner then is helping do its job with the damper actuator.
Right, and so not only can we sequence, but we gain additional thrust by use of a positioner. And really, when you see a lot of stiction, you definitely see it in dampers.